So the title sounds a bit complicated, so that's why I would like to walk you through a few projects that I brought with me. And yeah, at the end, I hope that you will figure out what I mean with this. But in essence, I would like to address a few points that have not been yet addressed yesterday. And this concerns spectroscopy, beyond-DFT workflows, and also some data analysis framework. So, as I said, I'd like to discuss three projects, or introduce three projects to you. One is an international one. It's a European Center of Excellence called NOMAD. And this is dedicated to bringing computational methods to the exascale. The second one is called FERMAT. It's a German-wide project, and it develops a data infrastructure, also called NOMAD. And then we have a third project, which is just a project within Germany, or not only with Germany, but even within Berlin. It's called FONDA. It's about the research of data workflows. And as I said, this is an initiative by the computer scientists in Berlin, and they have taken us on board as exemplary people from natural science projects. So let me nevertheless ask you, because these are very different projects to actually my research field, and that's why I would like to introduce what I am interested in general. So I'm a solid-state physicist, I'm a computational materials scientist, if you like, and we have a very strong focus on materials spectroscopy. So what we develop is methods and also code in order to describe, for instance, electronic structure. As you see here, this is the level alignment of an interface between organic and inorganic materials. We like to address optical spectroscopy, including electron-phonon interaction. Like this is the example of barium oxide, the perovskite material. Or likewise, we also look into core spectroscopy, where we combine these two with resonant inelastic Rig spectroscopy, as exemplified here for gallium oxide. Nevertheless, I'm not going to talk about this, but I just asked the question, why at all do I care then about workflows? Because we develop methods, we run calculations, and what else do we need than this? So let me take you to the first project, the NOMAD Center of Excellence. And this is, in fact, as I said, a project that develops computer codes, or to bring computer codes to exascale performance. Now, what is the question and what is the problem, in fact? What you see here in this graph is the system size that we can tackle with different methods. So if we go to the right, it concerns the accuracy of the method. And there you see, with density functional theory, at least with semi-local functionals, we can run systems of, let's say, 1,000 atoms or even more, thousands atoms. If you go to better functionals, the scaling is getting worse, and they become very comparable to Green's function methods for GW, for instance, that have a scaling of to the power of the 4th or 6th. So third power is very optimistic. But then if you even do better, like in employing coupled cluster theory, it scales with the 6th or 7th power in the number of atoms in the system, and then we can only do 10 atoms. So we go from 1,000 to 100 to 10. But the problem actually is, what limits us is that many materials and also many properties require more than just semi-local density functional theory, or they need larger system sizes. So let me start by the materials that we're interested in. So everything that's related to energy research, light harvesting, light emission, and things like that, requires better methodology or larger systems. So complex systems, I think we have heard about yesterday about alloys, but I like to show you another example where we need larger system sizes or unit cells. These are, for instance, these gemstones, right? So if you want to know what the color is about, then actually it's the same material. It's all aluminum oxide, but you replace 1 out of 1,000 atoms and the color would change. So if you want to describe the spectra, you have to go to systems that are larger than 1,000 atoms, or at least 1,000 atoms, but at the same time you need higher level methodology, right? So, in other words, what we have to do, we have to become better in both ways. So we have to go to better accuracy, but also to larger system sizes at the same time. And this is where exascale computing comes into play. So, and that's why I would like to introduce this project to you. Actually, it has several pillars. One of them is exascale codes, right? So, and exascale codes means that we like to bring density functionality, Green's function-based methods, and coupled cluster theory to the exascale. So we don't do this just for one code, but what we do is we develop libraries, because these libraries have two advantages. One is that libraries can be used by more than one code. And on the other side, we don't need to bother the scientists, because such libraries can then be adopted or optimized for a certain machine, for a certain computer architecture, and this can be done by computer experts. So we don't need to, this doesn't need to be done by the physicists, right? So these libraries actually will cover plane waves as basis sets, linearized augmented plane waves, and numerical atom center orbitals, and we're dealing with both with all electron codes and pseudopotentials. And these are actually what we call our demonstrator codes. So the libraries will be tested, of course, first with ABinit, which is a plane wave code. GPO is another pseudopotential code, whereas FHI-AIMS and exciting are all electron full potential codes. And let me just show you in 1 minute or in one slide what exciting is about. So this is the code that we develop in our group. It's an all-electron full potential program implementing the LAPW methods, and being all-electron full potential, we're able to even address core states. So like we have seen before, we can also compute core spectra, for instance, right? So we have a very strong focus actually on excited states. We like excitations. That's why we also developed the most exciting code on Earth. And so we will see a few examples of this in a minute. Well, not only in a minute, it's here in a second. So what you see here, these are two examples of core level spectra. This is methyl ammonium lead iodide, so it's the most fancy material for the new generation of solar cells, maybe, right? I'll come back to this. And what you see here is we can address all kinds of edges. This is, for instance, the L3 edge, so the excited states or the excitations come from p orbitals in iodine, or here the excitations come from d orbitals in lead. You see we can address very high energy energy ranges with our methodology. Now, this brings me to the next level, so to say, because in our network we also deal with exascale workflows. So it's needless to say that these let's say codes have to be run somehow, and to be run somehow needs workflows. And I would like to point out why we need workflows, in particular for excited states or for higher level methodology. So why is this so? These workflows, they serve as a glue. I always consider workflows as a glue because they control the computational parameters. And I have to say that excited states require many, many more computational parameters to be converged compared to a vanilla type density functional theory calculation. Workflows also combine tasks or recipes together. They can then be either executed in parallel or one after the other. They handle the jobs, because in high throughput initiatives, we have to make sure that all these calculations that we start have to end somehow error-free or error-corrected at the end. And at the end, workflows also put together, collect the results and the output files. And needless to say, so these workflows are very much method-specific, and to a large extent also code-specific, because every developer implements things in a different way, and depends very much on the code that you are using. So this is what the second pillar is actually about, and I would like to address this by the example of absorption spectra, of core spectra in a high-throughput manner. And how do we do this? So the spectra that you have seen before have been computed, what we call the Bethe-Salpeter equation. So if you go to the input file, it seems very easy, right? So give the job a name, you define the structure, you run a ground state calculation, and then you run an excited state calculation and choose the method for this Bethe-Salpeter equation, basically. So that's it. So in principle, you can hide everything from the user, but it's not a good idea, because there's so many knobs to control and so many parameters that you really have to know what you're doing, or you need to automatize it somehow. So this is the equation that we are solving. written down in an eigenvalue problem. You see here, this is a very complex, let's say, calculation. It depends on many parameters. And I would like to give you a little bit more of details to show you what is in there. So, but what is the physics of excitations, right? You have a band structure, conduction bands, valence band, core states. You shine in light, and this light actually excites an electron from an occupied state to an unoccupied state. And in optical excitations, this would look like this, right? So wherever you are in the Brillouin zone, you can initiate transitions from any type of valence band to any kind of conduction bands. And if the electron-hole interaction between the electron that has been excited and the hole that it has left behind is strong, such individual transitions, they can team up and they form an electron-hole pair, which is called an exciton. And for optical excitation, the corresponding wave function, which is now a two-particle wave function that depends on the coordinate of the electron and the coordinate of the hole, you can write down the wave function like this as products of valence functions and conduction particles, right? So you get this from the ground state. You build all kinds of combination, and then you let's say, diagonalization of the Hamiltonian decide what are the coupling constants in between. So far so good. You can actually also do the same for core states. This is what we have seen before. So again, you excite an electron, but now from a dedicated initial state to any kind of conduction band. Again, there are many possible transitions here. They can again team up to strongly or less strongly bound excitons. And in this case, these indices V and C correspond to core and conduction states here. So the only difference between optical and core excitations, this is a detail, is that you don't need to sum over valence states because you can address a single individual state because they're very far from each other. So, and at the end, you can compute the spectra out of it, and you see whatever you have computed up there, the peaks will appear at the transition energies, and the coupling coefficients also enter the intensity of the spectrum. So overall, you see already there's a few knobs to turn. So we have a lot of different indices here, but the situation is actually more complicated than you might think because there are several terms inside this Hamiltonian which are quite cumbersome. So I don't want to bother you with all the physics, but in essence, what you see here, there are different operators appearing. This is the dielectric screening, a non-local operator. Here we have another non-local operator, which is the Coulomb interaction between the electron and the hole. And you can imagine that treating all this is much more complicated than just the density and density functional theory. So in essence, if you go back to our input file, and don't worry if you can't read it, so there is a lot of parameters that we have to take care of in order to get a reasonable result. So, and for this, of course, workflows are very handy, and I like to introduce one to you, how to compute such a calculation or such a material. So you decide on the structure, you run a ground state calculation. So all this, of course, also comes with convergence tests and these kind of things. Then you decide on, for core states, the edge that you would like to address, then the species, lead or iodine or so, and the specific atom where the excitations should happen. Then you do a dry run for checking the parameters. Then you define the range of input values, so the range of parameters, and also the convergence criteria. I'll come back to this later on. And then you converge with respect to all these different parameters. And once you are done, you can upload your result to a database, and you can do further analysis with this. So far so good. If you have this, you can hide all the complexity from the user. Well, in order to do so, actually, it's always good to have some tools in hand that, of course, you can use, let's say, predefined workflow engines or workflows even, like ASE. There are programs for this, so we have heard about the materials project workflows yesterday. So you can use them, but it's always good to have a layer in between these ready-made workflows and recipes and your code to link them. So, and Exciting Tools is one of these layers. So it has parsers for more than 50 output files, so all these different things that the code can compute. and also tools for the post-processing of these results. It also has utilities built in for the input files, and it allows for easy integration into other workflow managers that are, for instance, supported by other groups or so. So the whole thing is written in Python, and it's also available on GitHub. So, but this is only one part of the whole story. So because there are other code pieces that are actually needed in order to finalize such calculations. So first we have the engine, so to say, the exciting that does all the numerical number crunching. Then we have exciting tools, which is this layer in between, let's say, the code and the higher level workflows. Then we have other workflows that puts together different recipes in order to compute a certain property that we're interested in. And then you can use any kind of engine that submits your job, like a job flow or fireworks or whatever, which guarantees then that everything is executed on an HPC machine. So, but having this said, of course, we are now working on benchmark data for core spectra, and this is particularly useful in our case because exciting is really a benchmark code. This has very, very high precision, being all electron full potential. So we are running our own calculations, but at the same time, we also teamed up with other groups. So you see here, this is an initiative by Dejolu from Brookhaven National Lab, but there's also John Vincent, for instance, from NIST included, because we wanted to know how good the agreement between different software packages is, right? So, and we're probing here different codes, and of course, also for this, you need a workflow, which is getting even more complicated because we have to serve 3 software packages. So exciting is all electron full potential, implementing the Bethe-Salpeter beta equation. Ocean also implements the Bethe-Salpeter beta equation, but on a pseudo-potential level. And X-Spectra is a built-in tool from Quantum Espresso, so Ocean can be linked to Abinit and Quantum Espresso, but X-Spectra has another approximation, namely the co-hole approximation. So it's not the Bethe-Salpeter that is solved, equation that is solved directly. So, and I'm not going into details, but we really made sure that all the codes can be run with the same level of accuracy, that we converge everything properly in order to find out whether the results really agree. So, and this is one of the results. So we have probed titanium K edge, so the 1s level of different titanium oxide structures. So these numbers here, don't worry, this is the materials ID from the materials project. And there you see that if you really bring it to the extreme scale, all the codes agree very well. In particular, exciting and ocean, both of them Bethe-Salpeter implementations. There are some deviations here and there by X-Spectra, but it's to be expected because the co-hole approximation is to some extent, or also very crude approximation sometimes. Anyway, I think the agreement at the end is very impressive. So there's another piece of software needed in order to run all this, and this is another little workflow called Lightshow, which actually creates all the input files for the 3 different codes at the same time. So let me just finish the NOMAD project by pointing out the 3rd pillar here. And this is big data analytics. So I'm not going into detail here, but I just like to point out that we also run a data analytics toolkit. Well, there should be a kit. There's a T missing here. And this toolkit is a collection of machine learning and data analysis tools that can be, well, operated on your own data or data that are inside the NOMAD database. And I think it's needless to say that data analysis and machine learning is also needs to be brought to the exascale in the sense that it should work in real time or near real time performance. So, for instance, if you like to use a machine learning tool in order to find out what should be the next material to be run in a high throughput manner, then you need to analyze all the materials that are already there, and you would like to not to wait for ages for the answer, but you would like to have the answer right away that tells you, okay, look at this material and not the other. So we're working here also on speeding up machine learning tools, and I'm not going into detail here, but this topic brings me already to the next project that I would like to introduce to you. So Jörg pointed out yesterday that in Germany there is an initiative by the Ministry of Science to make all research data fair. All means that there are about 30 different consortia from different research areas. These are bottom-up approaches, and each of the research fields can define what kind of infrastructure they need in order to make the researchers happy and make the data fair, right? So in Fermat is representing one of these research fields, namely the condensed matter and chemical physics of solids community. And what NOMAD, it's Fermat is doing actually, it builds and further develops the NOMAD infrastructure that we have just seen before to some extent here. So what is this infrastructure about? So maybe some of you know the NOMAD repository or the NOMAD laboratory, how we call it. So it started out already about 10 years ago with harvesting data or computational materials data and bringing it to the NOMAD database here, right? So what we are doing in Fermat now is we further develop this research infrastructure, right? And we further develop it not only with respect to computational materials science, but we also have an area of experimental characterization, another area of synthesis. So we are actually collecting and developing tools for all these different kinds of experimental probes and synthesis routes. But let me stay 1 minute or two first with the computational part. So also this computational part is extended, for instance, in terms of molecular dynamics and excited states that we just seen about. Just remind you that in the meantime, we have collected 140 million calculations. And well, some of them I would like to just show you in a nutshell here. So because if you have so many calculations, then I think it's also needless to say that some of them belong together. So if you do a geometry optimization, there are quite a few files that actually belong to this geometry optimization. And in that sense, we could either do backwards engineering and guess from the data which of the data belong together, or we can proactively implement workflows into the data infrastructure. And this is actually what we're doing. So what you see here is that if you go to the NOMAD database, then you see that you can select workflows. And if you select molecular dynamics, then you can see what are the different properties that we show here. And then you choose one of them, for instance, pressure. And then you see how the pressure, for instance, develops as a function of time. So you can analyze your data, everything that is uploaded there, also in terms of the workflows, and find out what belongs together. So, but as I just said, we not only work on theoretical data, but also on experimental data. And not only this, we also have an area of use cases, right? And one of our the use cases serve the purpose just to demonstrate or to show or to find out whether what we are developing is really useful for different, for a certain research field. And one of them is optoelectronics. And in particular, we're working on solar cells. So let me get back now to solar cell research and to a topic that is already discussed for quite a while, right? And the essence is whatever material you are interested in or whether application you're interested in, it takes ages from the invention of a material to bring it to the market. So in that sense, also from the invention of a solar cell material to the roof, there's a very long way. It's not high up, but it's really long way in time. And you see this is broken down in different, in terms of different families of materials. And you see they all have a, let's say, a more or less steep increase of the efficiency of the device. And I think the best efficiency that we have nowadays really comes from a special family of materials. These are the halide perovskites that I've just introduced you before, and they have a steeper curve. But if you look into the beginning, also it's also already 10 or 15 years ago, since this was the first let's say, discussed for solar cell materials. So the question is, how can we speed it up? I think many people think about this. And yeah, for this, I would like to take a step back and discuss a little bit with you what a typical workflow in solar cell research would be, right? So there are people here, they want to produce solar cells. So first, of course, they have to read all the literature in order to be knowledgeable on that. Well, once they have done this, they will synthesize a material. Once the material is synthesized, it will be characterized experimentally, then a device will be built, and a publication will be written, and then you close the loop, and there's yet another paper on the market, right? So I think, well, it's quite natural that all these processes are slow, right? Otherwise it wouldn't take that long. So let me go step by step and discuss the first one here. So this is another publication, well, that just appeared recently. I've taken it from this paper here. What you see is the number of publications, again broken down to different categories of or solar cell materials, and these are just publication on record efficiencies, right? So not all about characterization and so on. So just go to the right. What we see here, that we are dealing with the order of 100,000 publications. So, well, it's clear what this heap means. There's no person on Earth who can control and keep in mind what's going on in this field, and we're not even able to cite the most important work there because it's impossible to know it, right? So obviously something is going wrong, and we have to speed up the process here to make this process more efficient. In that sense, I like to introduce one, let's say, pioneering project to you. And this is, well, it's a community effort. You see, there are 100 authors involved. They have been reading 16,000 publications, and they have, by hand, digitized, so to say, 42,000 solar cells, right? So to bring everything into one publication at the end. So actually, it's a paper that appeared in Nature Energy 2022. So 42,000 devices, solar cells here, and of course they have defined all the metadata to describe these solar cells. They have added synthesis information. So it's a really very nice paper. However, a drawback is that this has a timestamp. So this paper was published in 2022, and how many students are you going to employ who would further read papers and put this into an updated version of this publication? So there's no way of doing this, so we have to think about a more clever concept, right? So,
just out of curiosity, is there a way to use some large language models to do all that?
I think
fine-tuned to work on
there are initiatives like this. In this case, I think they were really reading it and putting things in by hand. So, but yes, it can be automatized to a certain degree. So, yeah.
Would there be any peer pressure along the lines that if your paper, which is published after 2022, is not in the database, maybe you don't get cited that likely, so maybe that the authors of all the future papers themselves would add their stuff to your database?
Well, this is not yet a database. This is
it's not a database. You get
a publication, right? So this is a publication, and that's why a publication is difficult to update, because you would need to have forthcoming issues of this. So, and this is the well, the good news. But before this, I think there's another obstacle here, because they're very heterogeneous sources of information. So one of his publications, right? In this publication, you find efficiency tables, or in the other publication, we have 42,000 solar cells that are described. But there's much more on this market, on this planet. So some people already collect their information on databases. However, I think most of the information is somewhere hidden in the labs, because this could be either handwritten notebooks. This is already an elaborate one, so it's an electronic lab notebook, but this is still in the labs, and all the information is not public, right? So, in that sense, we have to bring together all these sources of information, and for this, you not only need workflows, but something more elaborate like a data infrastructure. So, the good news is that we have now all these 42,000 devices in the NOMAD infrastructure. So you can not only search for workflows, but you can also search for use cases. One of the use cases here are solar cells, and then you can see what all these devices are about, what the properties are. So I just show you a very small movie. Don't worry if you can't read everything. So the essence is that you can select materials according to the composition. Then you can actually look at some properties of the solar cells. You can somehow narrow the search by some filters, such that at the end you only find some data that you're particularly interested in. So, and I really need to point out this work was done by Pepe Marquez in this Fermat team. Here I enlarge one of these graphs, for instance. You can see here what is the efficiency as a function of circuit voltage, for instance. So that's one step that we managed somehow to speed up. What about the next one? So, I mean, synthesis obviously is also a very slow process because you have to decide what kind of materials you like to synthesize. And in these halide perovskites, there's a huge variety of just combinatorial synthesis to change one atom species against something else and see whether the efficiency improves. So that's why there's quite a few groups now doing this combinatorial synthesis, also high throughput characterization, because you want to know what the properties of these samples are. There are some labs that are already driven autonomously, and on top of this, there's also quite a few things that are done by AI to boost the whole thing. So still we have a problem, because what if you have such a lab, what are you doing with the data there, right? You don't want to upload them immediately to a database while you're still working on this. And our solution for this is what we call the NOMAD OASIS. So it's exactly the same software that is on the web, that you find on the web if you explore NOMAD, but you can install the same software inside your group or inside your lab or in your university, or for collaboration in a research network or something like this. So you don't need to make it public. It even works behind the firewalls of companies, and it's up to you what at the end you would like to share and make public at the end once everything is analyzed. So that's what steps 2. Step 3, making a device, is again slow, because now you have all the results of the combinatorial synthesis and characterization. So what kind of devices are you building now, right? And I would like to point out that also for this step, it's extremely important or beneficial to have a database. So why? Let's have a look at such a device. The device stack is such that you have the active material of the solar cell, then you have the contacts, up and on top and bottom, but in between you have these transport layers where the electrons and the holes are brought to the electrode, so to say. So, and of course these transport layers are also materials that we have to choose. So how does the database help? By this graph, for instance, this is not just a beautiful piece of art. I like it, it looks pretty, but it really serves some purpose. So this is a machine learning, a result of a machine learning thing, a graph that has 2,600 nodes and 3,100 edges. Okay, what does this mean? This 2,600 node is the number of transport layers, different materials that people have used for producing this 42,000 devices, right? So again, there's no person on Earth who can control what kind of transport layer you would like to use for a device, right? So, and again, machine learning tools like this and data tools in general can help you to get more insights than you would have with your naked eye.
Excuse me, just
yeah.
What is the meaning of the color scheme on this graph? Blue and red. I think this is different materials. Like, so here we have titanium oxide-based things. Here you have bead dot-based things. But I just wanted to point out to say what the key players are
in terms of this composition here. So this probably helps you to decide what kind of solar cell you would like to build. Now, having talked about, well, being a theoretical physicist, having talked about solar cells is probably not my research field. So what about calculations, right? In fact, I would very much like to do high throughput screening of all these different perovskite materials, because there are many of them. There are three-dimensional, two-dimensional, different molecules in between, inorganic components. So there's a variety again, and you would like to explore this also from a theoretical point of view. And well, high throughput in this case, for instance, searching for solar cells would be that the property you're interested in would be a band gap in the range of 1.2 electron volt or so, would be effective masses that are beneficial for transporting the carriers away efficiently. Property through would be, I don't know, like matter interaction, whatever you like. So you would like to explore this, let it through the funnel and see which of the materials actually are good for a solar cell. So I'm a little bit pessimistic on this, because if you want to do this on the DFT level, this is very problematic, because DFT would never give you the right electronic properties. We know all this. So you need to go better. And doing better, at this point, we don't have the capacity or to run really advanced methodology for these kind of materials on a large scale. So on a many-body level, such high-throughput screening is not feasible. And I would like to spend the next 3-4 minutes to point out that this is also problematic. And well, let me introduce one publication to you. We wrote a paper, kind of, I wouldn't say out of despair, but about the dilemma of choosing the right method for these kind of materials. And this was kind of a surprise. Why? Because we wanted to explore optical spectra of these materials, so solar cell research, right? And then let's say we wanted to be practical and say, go to the literature, check what functional is most appropriate to give you a reasonable band gap, and then we just compute the optical spectra on top of this. And well, to our surprise, this is what we found. So this is the band gap as a function of the alpha parameter of high-bit functionals. I'll tell you in a minute a little bit more about. So this is the experimental range. And this is the theoretical range that you can get. So basically, you can get everything you like. Right? So you choose a functional. If you want to have a band gap of 4 electron volt, go here. If you want to have a band gap of 1.4, go here. But it's the same material. So what's wrong here? Let me just stay with the left side here. So alpha equal to 0. So this is the mixing parameter of exact exchange in the high-bit functional. Just corresponds to semi-local functionals, local density approximation, gradient corrected functionals, right? Also here you see a spread of more than 1 electron volt. So what's wrong here? Because, well, some people compute this material with spin-orbit coupling and others don't, right? So if you don't, you end up with the conduction band here in the gray. If you do, it's getting lower by an appreciable amount of an electron volt, 0.6 electron volt or 0.7 electron volt, so it reduces the band gap. And well, if you don't include spin-orbit coupling, it looks like you get good agreement with experiments. So, but don't take this too seriously. So just keep in mind that there's a huge spread of results. So, but what about the others, right? Because if you have better functionals, in principle, you should be able to do better. Well, I don't walk you through everything, just summarize the essence, right? So we have employed 2 functionals, high-bit functionals, PBE0, that mixes in Hartree-Fock exchange, and HSEO6 that also mixes in Hartree-Fock exchange with this alpha parameter here. So what you see in green are the PBE results, PBE0 results. So you see there's a, well, starting, where am I? It died, yeah. So, okay, then I probably, does it disturb if I go here? So if you go to PBE0, you see there's a very steep increase in the band gap as a function of alpha. And now if you do better and do many body corrections on top of it, this is the GW method, the situation gets a little bit milder, so the increase is less steep, but still you have a huge starting point dependence. Thank you. So then if you go to HSE, the situation is the same, a huge increase, getting a little bit milder if you do GW. But these two curves never meet, actually. So you would need to go to insane mixing parameters in order to get rid of GW, right? And just to tell you, for cesium lead iodide, so for the perovskite, actually I didn't tell you, but this is just lead iodide, which is a precursor of this material. But you find exactly the same situation, bad situation for the perovskite materials. So, but the story is not over yet, because if you look at the HSE functional, thank you, there is actually a second parameter inside here, and this second parameter is a screening parameter. So consider the electron-electron interaction is very repulsive if two electrons are close to each other. This is why you need to have this exact exchange. But if you have electrons very far from each other, then this interaction is screened because there are so many different charges in between. So in that sense, you can also tune the screening parameter, so how far you go outside in order to damp away the screening. So now what the result, in fact, is then, if you take the screening parameter 0, this is the green line, it's just PBE 0 then. And if you take the screening parameter 0.11, then you end up with the HSE result. And in between, everything is possible. You can choose any kind of combination of these two parameters and get any kind of results with this. So this is very bad. So, and just to show you what happens if you then do it better, so you imply the GW correction. So situation, as we've seen, is getting milder, so the range of possible solutions is getting smaller, but still it's a very, very odd situation. Thank you very much. It's a very odd situation that yes, it does. That here, if you just want to use HSE, you need a mixing parameter of something like, it's very common for functionals, but if you would like to combine it with GW, you would need a mixing parameter which is insanely small. So obviously there's something wrong here, right? So, but I mean, to cut a long story short, what has this to do with workflows? Because if you now upload such results to a database, you need to know exactly what you have done, right? Otherwise, you wouldn't understand why you have a spread of several electron volts for one and the same material. Well, and at the same time, I wouldn't recommend to do machine learning on these materials if you don't know how to treat them. Right? So, but this actually takes me to the last project, which is FONDA. So what FONDA stands for is Foundation of Workflows for Large-Scale Scientific Data Analysis. So as said, this is a project that was initiated by our computer science department. It's really on the research of workflows. And we have a project in there. It's always combined projects between computer scientists and natural scientists. And our project is called Deriving Trust Levels from Multi-Choice Data Analysis Workflows. So what does this mean, actually? And in order to explain this, I like to go back to our NOMAD database, having this 140 million calculations inside. So obviously, there's no way that these calculations have been produced by one person, by one code, by one method, and one set of computational parameters, right? So we have all the variety there. And that's why also NOMAD is special, because we have invited the whole community to upload the data, whatever computer code they're using. So there are 40, 50 different computer codes that are used in the community. So there are 40, 50 computer codes. There are different approximation, different methods, different set of parameters that have been used for producing these results. Right? So in order to do machine learning, for instance, to learn from this, to develop new materials, you want to make sure that you only use data that are really compatible with each other. So this is the I-infer, the interoperability. And in essence, you want to know what the data quality is, what the purpose was the data have been produced for. So, and that's why our project deals all with validation and verification with data quality, and also somehow sampling or exploring the whole data space that is available in NOMAD. Now, in order to do so, of course, and to judge the data quality, you need to know first what the impact of a code, of a parameter, of a method is. Otherwise, you cannot measure it, right? So, and for this, we have introduced similarity measures. So, and I like to exemplify this with a spectral fingerprint here. So what do we do? So the example is just the density of states, but you can also do it for optical spectra. We have done this, right? So you have a density of states, which spans a certain energy range. You divide this energy range into different intervals. Then you integrate within each interval the density of state. This gives you a number per interval. And of course, you can tailor this fingerprint because you want to weight, for instance, this region more intensively than others. So you can use non-equidistant or equidistant bins. You can choose the energy range and the binning according to your needs. And then you can actually assign this integrated density of states to each bin. And then you get what you call a fingerprint, right? So this is the fingerprint that stands for this density of states. Now, in order to measure the difference between one and the other such spectra, we also have to introduce a metric that measures it. And in this case, we use the Tanimoto similarity coefficient. That means this is basically the overlap between the two different spectra. So if the spectra are identical, this coefficient is 1. If they have nothing to do with each other, this is 0. And the reality is somewhere in between. I'll show you an example in a minute from now. So for instance, now we can measure what the impact of the different methods for this material was. So go back to lead iodide. So start with PBE. This is the blue curve. Then we run an HSE calculation. HSE has increased the band gap, so the curve moves to the right. This is the purple curve now. So the overlap is getting smaller, and that's why the Tanimoto coefficient is only 0.6, right? So also we have differences here in the low energy range. Or alternatively, you can go from PBE to PBE, including spin-orbit coupling. There we know that the band gap has decreased, so the density of states moves to the left. Again, the Tanimoto coefficient goes to lower numbers. In essence, these two things cancel each other, right? So, but this is, as I said, just an artifact of the calculation. So now we have a tool in hand that allows us to measure the impact of parameters, of whatever you like, of methods, GW versus, don't know, any kind of DFT and things like that. We have done this. If you're interested, you can explore this paper down here. So, and that actually brings me now to the last point here, because actually the reason why we have implemented this fingerprint was not so much because we're interested in measuring data quality, but we wanted to know what are similar materials. Because if you have some metric, then you can find materials that are very similar to another one. And in particular, it would be useful for these lead iodides because they're toxic. So maybe this material will never make it to the roof, and you want to replace it with something that is not non-toxic. So, to be honest, we haven't found the solution because we don't have enough data there, and particularly not enough with the right data quality. But I still can give you an example here. So, you use this lead iodide as a reference. This is the density of state. And then we have scanned 1.9 million calculations in order to find out what the most similar ones are. And you see here from the distribution that the similarity with most of the material is very lousy, and there are just a few outliers here in this range, and these are the systems that we have here. So they have similarity coefficients of something like 0.8, and the others are already lower. And there's one material actually that doesn't have lead and looks similar. So, but this is just an outlook what we like to do in the near future. So, now let me wrap up. Just to repeat again that I've introduced 3 projects to you. One is a project that actually helps us to produce data with reasonable or with very good quality and fast codes. Another project that harvests the data and makes it ready for reuse. So this develops the NOMAD data infrastructure. And another project that allows us to measure data quality and explore data spaces. And this is the project Fonda. And if you like to explore your data space, you're invited to download or to get a NOMAD OASIS and to customize your own workflow. So you can implement whatever you like in this data infrastructure, your workflows, your tools, your analysis tools. Just explore it. And with this, thank you very much.
Thank you for